Hi, everyone. Thanks for being here. Good afternoon. I'll introduce my co-panelists. The topic of the discussion is the future of manufacturing. And manufacturing, as you know, is changing dramatically because of the innovation that we just talked about in the previous panel, AI, robotics, influencing manufacturing. There is a lot of pressure on supply chain from a resiliency point of view and localization point of view, and also sustainability. How do you do manufacturing but in a sustainable manner? So we have a great set of people from the industry. I'll welcome one by one, probably Professor SK, as he calls himself, Satyandra Gupta. He's a professor at University of Southern California, also co-founder of GrayMatter Robotics, doing very cutting-edge robotics work as applied to manufacturing. Professor, welcome. We have Peter. Peter is COO of Verdagy. They are doing very awesome work, innovative work in green hydrogen and electrolyzers that make it. Great experience before this at Tesla and before that at SunPower. Very well positioned to talk about manufacturing because he's actually a practitioner in doing it. Peter, welcome. And Charly, partner at Eclipse Capital, investing in companies which are actually shaping the future of manufacturing, robotics, automation as applied to manufacturing. He has a very interesting experience, investor, but several years in automotive, starting from traditional manufacturing at Toyota, Nissan, and then going to Tesla and Rivian. Great perspectives from him expected here. Charly, please come in. My name is Ravi. I'm investment director at TDK Ventures. So I think we'll just start by setting the stage on what the future of manufacturing and the factory of the future could look like. As all of you imagine, we are in 2025, let's say 2035, 2040. What could the future of factory look like? Probably a couple of lines from each one of you to start.
Sure. Yeah, so I mean, as you said, I'm professor at University of Southern California. I direct their Center for Advanced Manufacturing, and I'm also co-founder for GrayMatter Robotics, a company which is focused on robotic surface finishing and surface treatment. So from our perspective, factory of the future would include significant autonomous operations, so robots and as well as additive manufacturing and lots of other automation technologies will be there. And what the trend that we are seeing is that market changes very frequently. So we'll see this phenomena where people have to basically very quickly set up a factory, and then if the market demands were to change, then we have to be able to very quickly relocate it or reconfigure it to do different things. And that's going to be another feature that we will see. Environmental considerations are also there, so we have to make sure that we are extremely efficient from energy perspective, and as well as all the other aspects that go in running a factory in an environmentally sustainable way.
Very interesting. Peter?
Yeah, I think in addition to flexibility, which will be important, deployment of new technologies will make our factories continue to become simpler. So consolidation of processes, reduction of waste, and this is, as you've seen through the trends, right, which will continue. New technologies allow those things to continue to evolve. And I think we'll also see probably more domestic content, given the way the trends are working in the market at the moment. People are looking for closer, nearer sources of materials to come into their factories.
First, thanks for having us here. It's a pleasure to be here. We've been asking actually this question for the last sort of like 2 years since I left being an operator and I was a VC. And I was reaching out to a bunch of people from my network to kind of think about the same question you're asking. What is next-gen manufacturing? And there are many ways to look at it, but one way is to look at sort of like some of the trends that you've seen and connect the dots and extrapolate in the future and say, like, is this where manufacturing is going? So one of the key things, and I like to point out when we're thinking about that is, I came from 9 years of traditional automotive when I joined Tesla. And I like to say if people like me made up majority of people at Tesla, Tesla would be dead today. It was a happy medium of people who came from the industry, plus a bunch of people who came from outside the industry and started asking these questions about, like, why you're doing things the way you do. And so the interesting thing is, as we investigated levers to accelerate the entire value chain of manufacturing process, building the manufacturing systems, we found a lot of the answers in software. And so if you fast forward when we're thinking, again, building a ground-up team to do all manufacturing engineering at Tesla, at Rivian now, more than 40% of the team was software engineers. And so if you connect those dots, I think the future of manufacturing is software-defined manufacturing, right? I think that's an important part and touches on what SK and Peter talked about. And so when you double-click, what does that mean, software-defined manufacturing? I think there are like three distinct aspects of it. One is the process of going from a design to you can make the fast thing. And that process, from a manufacturing perspective, is you're going through this DFM process and the loops of design, which is probably typically long. And that whole process will be digitized and automated. It's just a matter of time. And you're continuously seeing a lot of people spending a lot of time there. And so that accelerates that process. And then there's a process that we forget and we don't talk a lot about, but there's a process of actually building the manufacturing system, building the machine that builds the machine. Yeah. And today it's anything but plug and play. The future of that, when we say software-defined manufacturing systems will become plug and play. Just like a printer, you connect a printer, we don't think about it 20 years ago. If you got a printer, it was an ordeal to get it to speak to your computer. And then the other part is what SK touched on is, okay, once you have this factory, how are they going to operate? And we're already seeing this trend. Anything that moves will be autonomous in the future. Cars are autonomous today. Factories are just distributed robotic system. They'll also be autonomous.
Great. Interesting themes, and we'll double-click one by one on each one of them. Probably let's try to visualize the factory floor itself and manufacturing of the next generation a little bit more. SK, you have described AI-driven robots that program themselves and from high-level descriptions. Can you unpack this concept for us and help us visualize what it means for manufacturing?
Sure. So if you think about traditionally, the way robots have been used in mass production, you will set up a line, people will go program the robots, and robot will just repeat pre-programmed motions. Now, if you really wanted to make any change, or if your product was exhibiting significant variability, you're out of luck. You have to spend now weeks fine-tuning things, right? Ultimately, we want robot to function the same way a human would. So, for example, you can go to a human sander and say, sand this part. Human will look at the part, understand its geometry. They don't even have a CAD model at that point, right? Or they're going to be even demanding a CAD model at that point. They'll look at it. They'll probably ask the question, what material this part made out of it. They'll have some process knowledge, and with which they'll go ahead and finish it. So our vision at the process level is the same. You will give the part to a robotic cell. You will specify what material this is made, and at some high level, you would describe that we want sanding to be done. The robot should be able to then scan the part, build its 3D model. Since it knows you have specified what material it is, it should then know how to go ahead and process it, and it should go ahead and perform the sanding for you. And should it run into any challenges or difficulty, for example, you said this is a carbon fiber part, start sanding it, and somebody has loaded aluminum part, robot should be smart enough at that point to come back and say, hey, this is not consistent. So then robots should be smart enough to debug problems and handle those as well. So that's kind of how the vision would look like, how robots will work in the factories. So whether it be sanding, polishing, grinding, painting, coating, sandblasting, welding, we envision the robots in the future will work in the factory the same way, where they'll be autonomous, get some high-level instruction, go work at it, and if something is not working right, then they will issue appropriate alerts and let people know.
I think a follow-up would be, what would the relationship be between humans and robots in this kind of a context, let's say 10 years hence?
Sure. So we believe that the physical work which is being done should not be done by humans, and the reason for it is a little bit different from my perspective. Robot can be 10 times faster and more efficient and deliver you better quality than any human can, right? Humans have a lot of constraints, how fast we can move, what we can see, what we can do. So I believe that all the physical tasks should be done by the robot. And robot can deliver superhuman performance in any manufacturing task. And if we look at the history of manufacturing, same thing has happened. If you look at injection molding or CNC machining or forging or die casting, none of these processes are copying what humans were doing. These processes were invented because these processes could give you dramatic boost in productivity. So all the physical tasks will be done by robot. That's kind of my thinking and our vision is. But however, there are lots of other issues which are related to what quality standard we should agree to, how that quality should be inspected, lots of stuff in the design, that factory is well balanced. A lot of stuff is going to be there around maintaining reconfigurability of the factory. So human will still have lots of role centered around definition of quality, design of factory, maintenance of factory. So lots of things that human will be able to do. But I believe that physical labor is something that humans should not be doing in the factory of the future.
Got it. Peter, I'll bring you in on a different aspect, which is designing for scale, and you are doing it at Verdagy. And you have actually talked in one of your blogs, and I was reading it about designing for scale from the get-go, especially when you were doing your factory for gigafactory for electrolyzers. How do these new process innovations change the way factories will be designed in the future?
Yeah, great question. So when we thought through implementation of manufacturing for electrolyzers, we took a fresh approach. So historically, electrolyzer cells were manufactured in fab shops, different components all around the world. Supply of materials would come from one country, go to another country. So the first thing we thought through was, delete and simplify. We don't need so many manufacturing nodes. So let's think about how do we consolidate all of that into the simplest possible form. And so we came to the conclusion that the right point in the value chain to sort of start our factory was nickel coils. And so an electrolyzer, the cell is 100% nickel. And so we partnered with a manufacturing company that produces feedstock for nickel coils domestically. So that became our input to our factory. And we said, from that point, inside these four walls, we need to make sure that we can produce our product without having a very complex supply chain. So that was sort of the first ecosystem optimization. Then inside the factory, we then came after every single process and said, how do we choose manufacturing processes that have already been proven and scaled and are appropriate for what we're doing? So instead of manual welding or manual metal forming, we went out to other industries and we said, air conditioning ducting does metal forming. Let's choose high volume scaled tools from that industry. So that got rid of the process complexity, and we ended up with 3 manufacturing lines that are all high precision, highly customized for what they do, the simplest form you could possibly get. And then the last thing we looked at was then how do you connect these things? And so our product is 3 meters by 1 meter. So to move it requires 4 people. So we looked at, classic conveyance. Classic conveyance is an absolute nightmare in a manufacturing facility. It's expensive, it constrains you on changes. And so we said, let's not do that. And so we went to autonomous mobile robots for the transfer of our parts from station to station. And so it brought in the element of flexibility. And so we ended up with a factory that from equipment arriving to first product was a month because we simplified the manufacturing footprint. We ended up with a cost of scale which was 5x less than our competition, which when you think through scale is an amazing advantage to be able to scale manufacturing capacity 5 times cheaper than everybody else. And so for us, that was our journey of getting to, how do you sort of rethink for scale in our industry.
Amazing examples of first principles thinking applied to reimagining manufacturing. And you would have done a lot of that at Tesla, or you would have seen that happening around you. Probably some examples from, and that is very relevant because Tesla reimagined manufacturing of automotive here first. So some examples would be very helpful for the audience who also has entrepreneurs in building factories.
From the Tesla days.
Yes.
Yeah. First of all, those are good results and impressive. A lot of people maybe don't know this, but early days, as far as the Tesla super early, 2012, I had to spell Tesla when I said where I worked back then. And many people don't know this, but Model S, Model X, Elon was actually famously not paying attention to manufacturing. As a matter of fact, when we were beginning Model X, was a meeting to discuss, manufacturing guys go to the studio to look at the concept for the Model X. Elon clearly told us our goal was to figure out what we needed to do, but not to give feedback on design for manufacturability. And so you fast forward a year and a half later, we're trying to ramp up Model X, and it was probably one of the most difficult vehicles, almost brought the company to its knees. So there was a whole rethink as we were starting, Model 3. And I remember the first time we were doing this design review, and we were actually challenged by Elon to rethink. Then I was leading the team that was responsible for the body of the vehicles, so the design of the body, but all the manufacturing systems as well. So design, product design and manufacturing engineering, vertically integrated all the way to design of the dies. And the challenge was rethink every aspect of manufacturing from our first principles. And the only answer for why you're doing something should be physics, right? It cannot be because, this is what you did before, or because you have to buy this off-the-shelf thing. And many people don't know this part of the story, but this is what led to, we're thinking about what are the levers that you could pull in manufacturing. And today it sounds obvious, like when Peter talks about it, but back then, just this conclusion that part consolidation was one of the most leveraged levers wasn't obvious then. And we were looking at things, density, velocity of robots, all these other things, and we found out if I'm building a table, you're building with 100 parts, I'm building with 1,000 parts, I'll never be able to compete with you.
Yeah.
And so that whole, that led us to think about even the body of the vehicle, like how do we reduce the number of parts from 600 parts to less parts? And that was our conclusion, but it was coupled with something else, and Elon actually gets credits for this. He says the method that you choose for part consolidation also has to be the method with the shortest value chain, so from raw material to finished goods. And this is really what led to large castings, which have become commonplace in automotive, but you can take the same principle and apply it to multiple other areas. In manufacturing or the manufacturing systems themselves, there's always opportunity to consolidate, to eliminate components. Yeah. So that's a good example.
Great. I can see a lot of parallels between how you're approaching things at Verdagy and what you did earlier. Let's get back to you with your investing lens. Manufacturing has always been considered as a very traditional sector, very capex heavy, more project finance or debt led. What makes it interesting from, as on today, from a venture style return perspective? What aspects of it are interesting from that point of view?
So I think many, not anyone in this room, but many people forget 80% of the global GDP is the physical industries,
Yeah.
right? So that alone tells you that there's massive opportunities there. But then you can look at the top 10 largest companies that do something in the physical space. So that's why. But we take a wider view. I think at a high level, manufacturing is just taking raw material and converting them to human consumable format. And everything in between is a version of manufacturing, whether it's supply chain, logistics, CapEx, all the things we talk about, automation. But then if you specifically think about the Western Hemisphere, even the US, the ecosystem has changed. So if you think about back then, like company like Tesla, and even most recently Rivian, you had to build a lot of the systems yourself just because you didn't have the partners. Now when I'm investing, I visited a robotics company, I want to say 2 years ago. And when I visited the robotics company, they were 4 months old. They had a prototype that they had built. And I asked them, where do you get your battery from? And they said they went online and they ordered their battery and it showed up. If you just think 10 years ago at Tesla, you knew the blood type of your supplier for batteries. So it was a very different world. I asked them where they had gotten their prototype shells from, and they said they were just 3D printed. Again, the technology has come far. Actuators, they bought actuators. We didn't have that option 10 years ago. So I think in the physical industries, whether you're doing robotics, you're getting into manufacturing, the ecosystem has matured significantly. And then there's examples of large successes, whether you're looking at SpaceX, you're looking at Tesla, and a bunch of other companies now, that there's a lot of talent. The last anecdote, sort of like a statistic here, one of the co-founders of one of our portfolio companies is the head of mechanical engineering school at MIT. He told me as recent as 4 years ago, I think like for every 100 graduates from, I think it was the mechanical engineering school, only 2 would go and build something in this space. And so today that number is 98%.
Wow. Okay.
In a short time. So it's remarkable. So there's talent coming into this space. Manufacturing has become sexy again. So you have a bunch of investors, tourist investors as well coming into the space. So, and the ecosystem has matured.
Got it. I'll continue with you because we are just shifting gears to supply chain, localization, reshoring, those kind of themes which are very pertinent now given the geopolitics and tariffs and so on, right? And there's a lot of uncertainty in the supply chain itself. And you have noted in one of your previous writings that companies are now seeking on or near-shored options for everything from raw materials to final assembly. What are obstacles to that today as a manufacturer based in developed economies like the US?
Like reshoring manufacturing? I think the challenge is, one, the ecosystem for manufacturing. So I talked about like ecosystem for building the technology exists. But when you think about just manufacturing itself, so if you're building a complex product, not a component, you're building a battery system, motors, you typically need not just you as an OEM, you need your tier 1, tier 2 kind of suppliers. And that ecosystem doesn't exist. And so, so then we need to build it. The muscle for building factories is something that we've lost, or rather it's not ubiquitous. There is a few of us who've been building factories in the US for the last maybe 20 or so years, but it's not common. And so when I became a VC, actually after being an operator for 18 years, for the first 6 months, I had more people reach out for help with manufacturing than for capital, which was shocking, right? And that kind of gave us this, sort of like insight. Like there are very few people to talk to who've actually done it, and so as a function of that, actually co-founded a company to be a contract manufacturer in the US.
Got it. Peter, you have built your own gigafactory, and right here in New Arc, you were saying, and probably some insights from your own learning of setting up large manufacturing facilities here would be very useful.
Yeah, so we had the advantage that on the East Bay there's a lot of existing people who've set up manufacturing, and so our experience was really easy. First of all, as I talked before, our manufacturing footprint, we simplified that to mean that we could fit our factory into a warehouse. And so the first thing was we didn't have to go and build a building and do a bunch of construction work. We could literally just find a warehouse hugely available in this area. The other thing that's hugely available in this area is talented people who know what they're doing on the manufacturing side. And so we were quickly able to build a very talented team of 10 to 20 people literally in months, just by tapping into the existing network of people in the area. I think there's very few areas in the world that you can do that. And then through that process, we then obviously brought in skilled equipment manufacturers or suppliers who knew their stuff and were able to leverage the capability that they had to rapidly get our manufacturing up and running. So that was sort of our journey. On top of that, we had a software platform. So we definitely learned, as was mentioned, the value of integrating software as we go. That's both from flexibility, but then also the end-to-end thinking of problem solving. So in manufacturing, it's very important to have quality control at every process, but you also need quality feedback from downstream, because if you're just looking at the individual unit, it's very easy to convince yourself something is massively important that it's actually irrelevant. So it's useful to have an end-to-end software system that allows you to sort of make sense of the world. And so, again, coming back to the people, we're able to find people who knew exactly how to do that in the area very quickly. So we had a really easy time setting up manufacturing just because of the location. The downside, of course, is manufacturing here is very expensive.
Yeah.
But for a first, new technology implementation, this is a great place to do it.
Got it. Thank you so much. We'll move to another theme, which is very close to you, SK, which is AI, robotics in manufacturing. What are the challenges right now, as you see, in making that mainstream? Where is it? What are the bottlenecks right now in seeing a lot more robotics and AI convergence happening with manufacturing?
Sure. So if you really want to get value or significant value out of deploying robots, the first thing that you have to stop doing is copying the way humans were doing things. So you want to really design systems which are going to fully leverage robot capabilities. So a lot of things that you see in the physical AI domain, where people try to collect data by doing teleops or watching videos of how humans were doing things. Unfortunately, neither of those modalities generate any useful data. Because if you want robot to do sanding 4 times faster, then going there and just watching how humans were doing sanding, or getting a human to teleoperate robot to do sanding would not be a useful path forward. So collecting the right kind of data so that then you can train the AI system and then fully leverage robotics becomes a challenge, right? So one has to now collect the right kind of data and then train the model. And also a purely data-driven approach is not going to be viable in this manufacturing domain. So what you would like to do would be the lots of physics-based models out there, which are pretty good, and you want to leverage them. However, they might be making some approximation. For example, let's say you take a look at your classical sanding model. The classical sanding model will pay attention to the force and RPM and the forward velocity and surface finish. But classical sanding is happening at slow enough a speed that it doesn't account for, let's say, temperature effects. It doesn't care that how the heating of sanding pad is going to create problems. But you're going to go 4x faster, temperature effect will become an important issue. So what you would like to do would be you'd want to take your physics-based model and then augment when necessary with data-driven approach. So you need basically the new architecture, which can marry these two words, which historically have not basically married together in the right way, or more in a more general way. People may have solved the problem for a specific instance, but in general, we don't know how to bring these two words together, right, in a consistent way. So I would say those are the two major right now challenges. How do you collect the right kind of data? Because a lot of process, unfortunately, simulation is not super accurate. I mean, we know very good rigid body simulation, but simulation is not super accurate. And therefore, you have to collect some physical data. You have to pay attention to sim to real gap, and you try to still make your simulation when you can. And then the right architecture where you can marry these two words of physics-based model and data-driven approaches. So those are the type of things that we need to pay attention if you want to fully leverage AI-powered robot and deliver value from those. So,
Peter, in your real case scenario right now, do you see very multifunctional robots or task-specific robots? What do you see is more practical and?
So it's right tool for right job. So we definitely have, I talked about autonomous robots for material transfer. We also have laser welding cells, which have programmable robots in them. Super helpful because it allows flexibility. One thing about bringing new products to market is product designers always change their mind. And you're always learning new things. And so if you set something up to be very rigid, it becomes very painful. So those areas that require flexibility, it's super helpful to have programmable manufacturing capabilities. There are other areas which, for example, we have roll forming as part of our process. We have that because it's high speed. It's also very repetitive. We're making a high volume of parts very quickly. That lends itself more to specialized tools, which the automation is custom built for that particular tool. And so, I think both have a place in the manufacturing space. You just have to pick the right tools for the right job.
Yeah. I think from the robot-human interaction point of view that you alluded to as Escape before, Charly, one question to you. Are you seeing a lot more work in new skill development to deal with this paradigm where humans are working with robots? New skill development to deal with this paradigm where you are working with robots on the shop floor?
I think not yet, only in the older paradigm of we do need more skilled people for single-purpose robots. I think in that sense, yes. But if you think about the kind of robots that SK is talking about, the whole idea is actually to lower the threshold from a technology perspective of interacting with robots, so they require less sort of specialized skills. But there's maybe an important point to talk about, because there's sort of like a dilemma when you think about next generation of automation, when you think about robotics. So if you take, like even our Fremont factory, where is here, California, where labor is expensive, the ratio of humans to robots is something like 5-1, right? Like, so it's still a long tail of tasks that are not automated. And if you take all the tasks that happens in a factory, manufacturing factory, the tasks that are unsafe are always automated, right? Lifting a vehicle from one floor to the other, it doesn't matter. You're not going to throw people at it. That's automated. And then there's tasks that are high density, volumetric density, meaning you're doing the same thing over a unit of space. You apply industrial automation. It's best suited for that. But then the interesting part is, like, if you look at these long tail of tasks that are not automated, they're easy for human beings to do. They're low density and volumetrically distributed. And so if you do a bottoms-up analysis, it means you need something that can do multiple tasks and that is mobile.
Yeah.
There's many two schools of thought there. There are people who think humanoid is the only answer, but I think like it's multiple form factors. Yeah. But the key thing, and I think that's what SK was talking about, is if you develop this human-like intelligence applied to any of these form factors, you do get huge benefits. And I think like that is the future of automation. By definition, that automation is easier to interact with, easier to teach, easier to reconfigure, and therefore lowers the threshold from a skill perspective.
Got it. Great. Thank you so much. We'll move to the next section, which is on sustainability, which is one of the core pieces which the industry is wanting to get to. And Peter, you're best positioned to start off, which is, you are trying to achieve fossil, parity costs. And once that happens, what does it do to the ecosystem when you have abundant fossil fuel parity energy, let's say hydrogen?
Yeah, so, we talked earlier about, Charlie had the perspective of like manufacturing is taking raw materials and converting them into usable items. The key other ingredient in that equation is energy, right? And so if you think through our use of energy, like energy consumption is ever increasing. And so when you think through what, for example, solar has been able to do, solar has been able to get to the point where it's the cheapest form of energy. And so, the cheapest form to scale. That is unlocking our ability to do a bunch of things that we couldn't do before. And so for us, what we're focused on is the same thing in hard-to-abate industries. So we're using hydrogen to unlock, as you mentioned, fossil parities so that we can see the same kind of effect and energy availability for industries that can't electrify, but still need the benefits of reduced cost of energy. And so I think it's just going to allow us to do a lot more things cheaper, is the basic equation, right? Cheaper energy is good for everybody.
Percolates down.
Yes.
Yeah. Charlie, from an investor's perspective, right, do you see the framing of sustainability more as a cost center or as a differentiator?
I don't know. To be honest, I don't know. I think you do have maybe large companies who approach it as a cost center, and then you do have, startups. Verdagy is a good example who are approaching it as a revenue opportunity, an opportunity to make something differentiated. So the right answer is actually I have no idea. We're seeing both play out. I think manufacturing before was only optimizing for like three things: cost, quality, and time. And now everyone is thinking about carbon footprint.
Yeah.
But it's almost like ingrained in our thinking. And so we're not outrightly calling it out. No one, Rivian didn't come out and say we're just a pure sustainability company, but that's the underpinning of the company. Tesla didn't come out and say that. And I'm seeing pretty much a bunch of manufacturing companies, and that's the approach today.
Yeah.
So I think
one of the consideration, not a pure play consideration.
A core consideration.
Yeah.
I think it's become completely ingrained, and so people are no longer like blind to the impact of sort of like the impact of manufacturing on sustainability, on climate, and so I think it's become sort of like commonplace today.
Great, thank you. I think those were some of the themes that we wanted to cover. We'll open it up for some audience questions, but before that, just summarizing some of the takeaways from what all of you said. One, reinvention versus optimization, first principle thinking, etc., can make this manufacturing go 100x, like we aspire to do. The other was on localization, right? Simplified ecosystem maturity, etc., will enable manufacturing to be very different, distributed, and resilient. And sustainability, like you said, is fully ingrained in the approach, not afterthought or not the core itself. Fossil fuel parity gives a huge strategic advantage, cost advantage, because it's the core material. So thank you so much for sharing your thoughts. I'll we have 5 minutes to go. So
thanks for the discussion. Paul Schenk from Fathom Fund. Maybe question to Charlie. What's the future for additive manufacturing, and what would it take to bring that in more in the mainstream?
I think additive manufacturing is the future, right? If you think about maybe the earlier discussion example I gave, actually, we rarely talk about this, but if you take something as complicated as a body of a vehicle, which is made of hundreds of parts, our initial conclusion was the best way to actually manufacture it was through additive manufacturing. sort of like the best piece is one piece. The challenge back then, this is almost 9 years ago, is the technology was not as mature as it is today. And so there are a couple of companies. So if you're aware of a company called Vulcan Forms, which is based in Boston, they've made a lot of headway in solving a couple of the things that were challenges in manufacturing, meaning speed was a huge bottleneck. They've solved that. Second was getting mechanical and properties that were at par with traditional manufacturing methods and doing that in a robust way. They solved that. And also ability just to scale from a performance perspective. And that was actually less to do with the technology than the software that precedes the technology so that you can use this efficiently. So I think that, we'll just continue seeing more additive and, kind of transferring from like forging to traditional sheet metal stamping processes and going towards metals additive, and then obviously other materials as well. But it's inherently an advantage process. It's, I think like the broader question for me, I think the future of manufacturing, everything we're saying is good when we talk about, we pay attention to 3 inputs to manufacturing. There's electrons, atoms, and today there's bits, right, software. And we talk about electrons. Peter talked about being responsible in terms of where the electrons are coming from. We don't talk enough about the atoms. And today we're okay with buying something here in the US, which is metal. But that atom has traveled something like 20,000 miles around the world just to get to that finished product. When you don't care about carbon footprint, it doesn't matter. Then you follow an optimization for cost path. But when you do care about carbon footprint, the best way to manufacture is to do it locally and to pick a method with the shortest value chain from raw material to finished product. And additive is one of those products or processes.
Any other questions?
Hi, Manu from Ethereal Exploration Guild. Just an extension to the question. From an additive manufacturing standpoint, so we look at DED and then you look at PBF. So in a powder bed fusion, do you really see this scale being reached in terms of the dimensionality in terms of height? Do you see that scale being achieved with the current limitations of optics and thermal management in the next 10 years?
I hope so, but I will say I'm not a subject matter expert when it comes to additive by any means, but I can tell you that we do have a couple of companies in our portfolio who are, again, I think like this is where we go to some fundamental points that you made. If you double click on the issues that we're talking about, the additive manufacturing was limited to smaller components of parts because of things like this. One is structural consistency. Second was thermal management, depending on how you're doing it. But then today, what you're seeing as a key unlocks is not even in the process as the understanding, the fact that you can do better thermal simulation today, you can develop better material that can deal with thermal dissipation, and those things are unlocking. So what I'm seeing improvement on is materials, understanding of those materials, software, huge improvement in terms of software to enable these capabilities and even improve upon our understanding. And then when you look across the technology stack, everything from laser, the optics, they're all becoming increasingly cheaper and more performant.
So, yeah, maybe I can just add a little bit because we do fair bit of powder fusion, based AM in my lab. Basically, right now, I think the optics and laser challenges can be solved technologically. Challenge right now is that the powders are so expensive that it's difficult to make a case that a really large part you would produce it using powder bed type of process. Economically, it would not make sense because of economics of it, right? The materials are so expensive. Moreover, if you're trying to create a really large part, the risk that becomes that you will introduce some defect somewhere, because more layers you do, more area you cover, more odds are there that you will introduce some defect. And then the risk also then makes things quite challenging, right? So technology perspective, people can build a machine if you wanted to print really large part using powder bed fusion. However, right now, unless the material costs tend to be more reasonable, and if we can give people real assurances that the probability of us introducing any defect are going to be very, very low, it's going to be difficult to make a case that why would build such a machine.
Thank you. Thank you all for coming, joining us. Thank you.